Hello and welcome. I'm Bill Wake. We're here working on an Elm interpreter written in Swift. Up until now, we've been working with an approach called Parser Combinators, and it's been interesting, but I think we're switching directions today. So there's things I like about it, and there's things I don't like, and there's things that are going to work and things that aren't going to work. So it's one of those. Um, Definitely an interesting approach, and the benefit of it is you get this very straightforward map from your grammar to your parser. So once you have all these parser combinators defined, you can they're very similar to just writing a regular grammar. We used ampersand and or bar to represent sequence and alternatives. You can do that. You can have a few other operators that make things straightforward, and it's very nice in that sense. The One of the challenges is it's hard to debug. So we have these parser combinators. They're defining basically functions returning functions and then wrapping them all together with functions, you know, merging them and accumulating them and returning functions that return functions that return functions and so on. Mostly you get to ignore that because it's so readable, but when it's not working, oh, it's a pain. Okay. And what I did last night, I dug deeper into some of these papers. So I've had this tension. I've been trying to learn enough to let myself sort of try and do it from scratch as if I invented it when I clearly didn't. Um, and sort of struggle through these things versus taking a pre-given solution that's in a paper somewhere. And so I use these papers for inspiration, try and get just another hint from them and figure things out. But I dug deeper into one of the better papers, and one of the things that came out of it was that basically this approach works better for lazy evaluation languages. So um, in a in a well, in a typical programming language, I guess I'll say it that way. You know, your Fortrans, your C, your everything up through Swift and lots of modern languages. Um, the certainly in all the imperative ones, the tendency is that if you get two alternatives, you evaluate them, and if you're generating something to fill up an array, you fill up the array, and if the array is big, you got a big array. Okay, the lazy approach says don't put anything in there unless you need it, and so as the sort of regular programming languages, Java, C Sharp, Swift, have moved into the kind of functional pipeline sort of approach, you see hints of that coming through. That you can deal with infinite sequences as long as you never try and get the whole thing. Okay, if you want to count the number of numbers, you're in trouble. If you just want to get the next one until some criteria, you're probably okay. And the lazy evaluation says, just don't evaluate until it's actually called for. And some of the functional languages, I mean, Haskell clearly was one of the earlier ones that explored this approach, and they they have the advantage in these kind of parsers. So basically, these parsers can generate all the alternatives that might apply, and that's great. It means we build this sort of spreading tree of possible parses and throw out the ones that just kind of don't work in the end. Um, but in a lazy evaluation language, you don't have to build that whole tree. You're just building the ones you need to look at, and you find just enough, and either you find just enough to learn. Oh, this pathway won't work. So throw that one out, go to the next one, and eventually you find the one that does if there is one. Okay. Um, and the alternative in the imperative languages, if we're generating everything, is we generate these big structures and then throw away a bunch of stuff. Clearly not a great approach from a performance point of view. And one of the nice papers I looked at was I forget the guy's name now. Sorry. Yasuhiro Inami had a nice one called Parser Combinators in Swift, and he developed examples along the lines of what we're doing. But I noticed when I went to his library that he developed, and lots of places in there he had to go like, oh, we'll do it this way because the actual functional way is just too slow. And so all kinds of times we saw that going. And then the other paper I looked at was Hutton and Meyer, and that's an excellent paper about the approach. I think we'll steal some of the ideas later on, but for now, this is this is a starting point. And they definitely pointed out this notion of using a lazy evaluation. And the example they gave is the one we struggled with yesterday. So if you remember yesterday, we were doing these nested comments, and you had brace dash and then a bunch of stuff and then dash brace. Well, the bunch of stuff might be a bunch of dashes. And so we tried matching zero or more dashes followed by dash brace. Well, it if you the way we did it, we did greedy parsing, meaning you had dash star, meaning zero or more. We would grab as many as we could, and we ended up grabbing the one that was part of the closing brace. And we at the end of the day yesterday we figured out some way around that, by changing the grammar and playing with it differently. But the fact is that that sort of hurt us. I mean, we want to write this very natural grammar, and here we are mucking around with it and worrying about look ahead and all that kind of stuff. And so it just was clear that's not going to work. So what they do in the more functional approach, they generate the list of all the matches. So we say one or more, zero or more. Okay, they will generate, like in our case, maybe you have three dashes in a row and then the brace. They generate the parse that says three dashes, or two dashes, or one dash, or no dashes. Okay, that's the meaning of zero or more. Okay, kind of in the context of what we see in our text of three dashes in a row. And their idea is then that you take the list of all possible parses and you get that list. And then if you're sequencing it, you take the list of parses for that thing, which in our case is dash brace. I guess this way for you. You take those two lists, and then when you do a sequence operator on them, you try and match up the ones that will work. And the only one that's going to work is the one that finds two dashes and then a dash brace, and then that sort of folds it down. I get it, but I think I'm making a command decision here, I guess, that I'm not going to take that approach. We've spent a couple weeks on it now, which is I don't know, 15 hours maybe total, 12, I don't know, whatever it works out to. It's far less than a week's work of full time, but it's been a good experiment. But I'm going to say we're going to push a little further and then call it a wrap. So, and I don't know if it gets tricky, I won't even do that. It's like the first roadblock we're going to give up, I guess, because I'm planning to give up on the approach at any rate. So I'm not gonna fight through for an hour. So I want to spend like, I don't know, maybe let's just spend till our break. So give or take 20, 30 minutes, something like that. And just see if we can kind of work in the approach they do. The problem I have at this point is their approach generates these arrays of possible parses. So if you remember, a parse looks like, here's the item I found at the front, and here's the rest of the input stream. So it's a tuple, a duple. All right, so let's get to it. All right, I did not run yet this morning, so let me just kick off these tests, and we'll look at the code while we're testing. Okay, so in the approach, we want match a Boolean function choosing a parser that yields characters. That's fine. Where it gets messy, I guess our many is probably the place to look. Okay, so many one. Well, what we did, yeah, so this thing is just the greedy thing. Okay. Yeah, so what I really want to do, see, I want my return value. I don't want an array of stuff. I want my parser to produce an array on the outside. Okay. I want to return an array of parsers. So I'm going to define a new one. That seems the safest. Okay. And this is pure spike stuff. So we'll be fast and loose here. Okay, we'll make an extension. And this will be var, we'll call it M1. Or how about one or more? And it's going to produce an array of parsers of returning A in a bracket. Yikes. Okay. And I'm just going to steal the code. Oops, I forgot the first line. Okay, input in. Combined extension must be declared on the unspecialized pressure. Have I got my braces right? Oh, I don't see the issue there. Oh, one more brace. Okay, let's see. Our inner stuff. Here's repeat. Input. This. Parser. I'm skeptical. The error went away because I clicked there. Okay. Now this, we're going to return an array of parsers. I'm already... Okay, let's make this result of parser of... it might be like this. Maybe don't need these inner braces. Oh, golly. Cannot convert return type. Closure expression unused. Okay. Parser of A equals that. Return. Well, we're going to return the result in the end. I may be messing myself up with these names, but okay. This should be all right now. Cannot convert parser of A dot type to return type parser of A. Oh, he's not a parser. Oh boy. Okay. Let's take the non-extension approach. Let's make a function. One or more, it takes in a parser of A. Okay. And then it returns Okay, so let's see if we got our types right. We take in a parser of type A. and we're going to produce a bunch of parsers of an array of parsers of A. So I think I don't know. I'm going on a weird path. Let me see. Okay, I'm pulling up this Meyer paper, Hutton and Meyer, and their parser is returns tree strings. So their declaration, yeah, maybe this is too much work. They do this. They do type parser equals string. Well, first they do this, and they say, if you had a parser that produced string to tree, okay, but that where tree is the result value that you want from your parse. So you're just saying a parser takes in a string and produces a data structure. In our case, we would say AST, abstract syntax tree, but maybe tree's better. And then they say, well, that's probably not good enough, okay, because one thing that can happen is, you'd like to be able to see the thing you're getting back and the rest of the string. So your parser doesn't have to parse the whole thing. We can have parsers that just parse one thing and then tell us the rest of the input. Okay. And then they say, well, that's not going to work for our purposes because you can have multiple parses that qualify from the same thing. And so their parser looks like this. For their parser combinators. It's a parser is a thing that produces these pairs of tree strings corresponding to the fact that you might have one or more values resulting. Okay, and so I guess what this is saying is we don't get a bunch of parsers out. We get the whole thing is a parser. It produces an array of these things. Now that makes this a parser. Okay, so it's going to produce my input in our case. Okay. We don't parse strings. We're parsing my inputs. So a parser producing A really we want this thing to be an array. Okay. Now I think I'm going to give up then because there's too much other code we have that assumes our initial definition optional. So in this model, you have an input and you produce the item you want, whatever type that is, and the rest of the input, and it's optional. Optional being either passes or fails. And if it passes, you get that stuff. If it fails to parse, you get nil. And if I modify this, the modified approach, and I may just go down the pathways, I don't know, we get, it's an array of pairs, A input. So this would be the equivalent. And then everything's going to break because nothing produces this right now. Okay, all these parsers produce a parser of a parser returning arrays of A and stuff like that. But a parser has to be producing an array of pairs A and input. Oh boy. Well, Yeah, I don't know if I'm just gonna whack around on it. A parser of character, then, with this definition, is a parser that takes in some input and produces an array of with outputs of characters. Okay, and you can see where this would work nicely for our many one, because we would have dash 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 comma input starting at after the dash. Okay, the cursor, if you will. And we would have another entry that's dash dash with the cursor starting at the dash before the brace. And then other ones that's one dash with the cursor starting before dash dash brace. Is that too crazy? Okay, so we'd get this with, let's say it's position 7. Well, no, let's just say the rest of the input is brace, etc. And we'd get this pair that's dash dash with the input being dash brace, etc. And we'd get dash. I'm terrible with parentheses. Okay. We get dash with the input being dash dash brace, etc. And we'd get input nothing, or we accept nothing for the optional case, and the input is unchanged. Okay. So we would like our many of star, many of star, or many of dash, too tangled up in the punctuation. If you have one dash, we would like to be able to have 0 more dashes followed by dash brace. Okay. Given the input string dash 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 brace, okay, we can see that this one is not going to find, and I guess our parse is sequence, well, let's say I'm going to use prefix notation. Many of dash followed by literal dash brace. That's our grammar, something like that. Okay, so 0 more dashes followed by dash brace. Okay, and if you look at this, if this is the result of the many, this giant array, okay, when we go to append it with literal dash brace, okay, it's going to take the rest. The definition of sequence is take the first and then take the rest from the first and try it out. Okay, and so it takes the many and it gets this part and then says, okay, now I try the literal on brace, etc. Doesn't work. Toss it. Try this one. Here's the many, brace, dash brace, etc. Oh, that looks good. That's fine. Keep it. Dash followed by dash dash, etc. Does that match dash brace? No. Throw it out. Empty string followed by dash dash dash. Does it match dash brace? No. Throw it out. So all we're left with is an array of one item. Okay. And and then our parse can continue on from there. So the reason why am I hesitating? I guess I gotta address that. Well, there's gonna be lots of places with minis, and I'm thinking of, like, you get some big expression, A plus B plus C plus D plus E. Okay, well, each one of those is going to be an option. We could have 1, we could have A, or A plus B, or A plus B plus C, or A plus C plus D plus whatever. All these things carry around. Every layer that has repetition, it's going to generate more and more of these things. And I don't know, it just feels like a struggle. And part of it is I'm sort of in this mode of framework writers everywhere. Okay. I would like a parser combinator framework. If I had that and I could go find one, I could try Parsec or one of these other ones and use it and plug in my stuff and go. And that would be fine. I don't know. It's not what I'm trying to do. I'm trying to kind of create one from scratch, as it were. Although I'm building on Swift, so there's a lot of scratch there. But It doesn't feel incremental to me, so I dislike it for that reason. So I have enough experience with parsers and scanners and stuff like that that I'm pretty confident I can take the next case statement or if statement or whatever the next thing we want to tackle is and build in the parser for that. That sounds pretty straightforward. The combinator approach, it sounds like I'm going to be messing with combinators for days to do it. And my goal is I wanted to learn about parser combinators. I've learned a lot. I haven't learned everything clearly, but I met that part of my goal, the learning part. There would be something to be said for pushing through, but on the other hand, this project is to write an Elm interpreter. It's not to write a parser combinator, and so I'm left wanting to get down to different problems, I guess. I mean, I still don't know much about Elm's real deep rules for interpretation of things. Like I don't even know. Honestly, I don't even know if Elm is lazy or not. I don't think it's come up for me. Um, I worked through Richard Feldman's book last year sometime. I was like, oh, this is very cool, but that doesn't stick in my brain as to whether it's this or that, So clearly there's a bunch of stuff I've got to learn about Elm. So, maybe this is just justifying, but I think I'm going to revert. Let's see if I can do that properly. Okay, we did get all our tests passing, which is cool. Let's make sure what's going on here. Okay, let's do some diffs. Okay, that's our stuff. I think that's just incidental complaints because of the junk I left up here. Let me comment that out. At least try and get the rest of the input to do its thing. Okay, so all this stuff. Yeah, that junk. Okay, so I will safely do that. Elm parser. That I might let be. I clearly did not check in the last bit of stuff yesterday. Okay. So I'm gonna be a little more manual in what I rip out. I'm gonna try and rip out everything I put in today and do a diff and get a clean diff. Okay, so this stuff can go. Okay, this goes back. Hopefully that makes everybody happy. Yep. These can go. Actually, all this can go. And let's diff this. Match 1 we added yesterday. Okay, so let's run these tests. Okay, let's commit this. So we made some nestable comments. You don't like nestable comments work? We didn't finish it by any stretch. Okay, but all right. Cool. So wow, I want to take a very different approach. So a lot of this stuff's going to go away, basically. The thing I have so far, right? I've got integer literal is a parser that you give it string and it produces the literal and the rest of the stuff. Okay. The approach I want to move to, I'm just going to go to the old standby like recursive descent parsing and with a separate scanner. Okay, so I'm going to write something. Basically, the stuff we've done so far is normally the domain of a scanner. A scanner builds around mostly regular expressions, some exceptions, but mostly regular expressions, and pulls apart things like integer literal versus float literal. Okay. And so let's so I don't want to break the Elm parser versus parser may not be useful. Okay, because what I'm calling Elm parser, I think right now is really my Lexer. And I want to do it a little differently. I don't know. This is so lovely, though. These conversions and stuff like that. Oh, it's really nice. But I'm going to take a different approach. All right. So what I'm going to do. Let's see. What I want to do is define I'll call it Lexer, lexical analyzer, and I'm going to give it input. So something. It's sort of like this. A Lexer is going to take. It's going to take strings. Let's say a string, and it's going to turn it into a list of tokens. Okay. And I think we've kind of what we're calling these parsers really correspond more to our tokens at some level. Okay. So let's see. So yeah, and then later on, your parser is going to take a list of tokens or a stream of tokens and produce an AST, abstract syntax tree. And maybe abstract syntax tree isn't even the right name. Maybe tree is just a better way to go. It sort of didn't seem to be taken. Okay, but it's a token. It's going to turn the list of tokens into a tree of some sort, and then the interpreter is going to take a tree and then produce. Well, it's really a string. Okay, it's like all that work to get from a string to a string, but that's basically what a programming language is going to do in our conception. It's actually going to produce behavior. Okay, but you're going to see output. Okay, in a REPL. So you put in a string that's the code. It transforms it to a list of tokens, transforms that to a tree. The interpreter takes the tree, evaluates it, and comes up with the output that it's going to put in the REPL. And it's got its own stuff going on there. Okay. And so let's see. So I'm going to go back to kind of first. Well, I'm going to rename this file. Okay, so do I just type? Let's call this lexer.swift. Okay. And then Elm parser test. Did my parser test was... Oh, I broke them apart. Okay, integer tests and things like that. Okay, so let's define a type, and I'm just gonna pick it up in here, and we'll eventually trim stuff as we go. So I want to define an enum. Let's see. We had one. Where's our interpreter? Okay, AST. Okay, yeah, enum name cases, right. Okay, the name is going to be token, and it's going to have a bunch of cases. All right, And we can hold off on the cases for now, for the moment. Okay, so let's add a Lexer test and go from there. You know, I just don't like doing this. Let's just take this one. Okay. We'll revise this test name, but this is normally a good time for a break. So we'll take a 2-minute break, and we'll come back and see what we can do. I have a feeling we're going to mostly catch up today. I mean, we got a couple hours yet, basically. We'll catch up, get the tokenizer working, and maybe see if we can go a little further. All right, so 2 minutes. Thanks. Hello, welcome back. All right, so let's see. We left off. We've got this nothing Lexer. All right, and I think what I'm gonna do is basically start with emptiness. All right, because handling an empty file or the end of the file is kind of a tricky bit, and the easiest way I know is some sort of sentinel value. So we will do that. I don't know the Elm. I don't know its specific requirements enough to know what's safe or not safe. But um, let's say test empty input returns end of file token, end token. I don't know if we got the word end anywhere. Let's see. We should have a better name for this. I don't know. End file. Well, we'll work on that name. All right. The assertion is going to be it's going to be something like token dot whatever this thing's called end and it's going to be, let's call it result. Okay, so token and generic parser a. Okay, let's define, oh, is end allowed? Case end stream, end input, end file. What else can we call it? Right end, bottom. I'm going to call it EOF. I don't know. EOF. End of file. I don't know. That's such an abbreviation I've known for so long. I hope it's a standard one for people. All right. And so somehow my token, well, let's say tokenizer, generic parameter A could not be referred. Okay, yeah. I'm going to say token Lexer equal Lexer. Do I want to give it input? Yeah, let's do that. Nothing. Okay. then we're going to look at result is really Lexer dot, I don't know what we want to say, get. We're going to have to, well, it's subject to refinement as always. Okay, let's frame it in so we don't have a class Lexer, or maybe it's even, I don't know, like, does it need to be a class? Maybe it's, no, it does. Okay, so let's do class Lexer. And it's got to have a function get returning a token. Okay, and I'll just put some, let's see, wrong. We'll just add it temporarily just to, does that work? Token wrong. I never know when it knows you can use it implicitly. It just seems random to me, but okay. This test should fail. Okay. And then okay, I'll complain about var maybe. All right. All right, EOF not equal to wrong. Okay. Let's return EOF. That weird background, I guess it's just that. Yeah, let's, I don't know why the IDE wants to be transparent, but it does apparently. Okay, so you feed in no input, you get an EOF. Let's how's this gonna work? Well, maybe the next thing will reveal it. If you don't do anything, well, okay, let's make sure our, let's work on our integers. Where's our parser tests? Integer tests. All right, I'm going to move these over. I'm going to close this. Lexer tests. Okay, so we did a parse digit matches multiple digits. So we jumped right in. Okay. Let's start with one digit. Okay. All right, so the Lexer is a Lexer of 9. And we expect a token.int. Well, with expression lexer.get. Okay, it has no value int. Let's make one. And run. Okay, int is not equal to EOF. All right, so our get function now, this thing is going to be the heart of it. All right, so what we want to do is take the first thing off the string and switch on that. Okay, now, so you can see already we're hitting this end of file input thing. I would like to, well, can I go to Parser? Where's my input? I think it's in Parser. Yeah, let's do this. Let's let it go through my input. I think we'll work with that. Okay, so this is going to be my input, and we'll maybe pass it in at some point, but just to kind of get through things here. Okay, and I want to say switch input dot first. And I'm going to do some stuff. Okay, and if this thing is a digit, okay, I'm going to do something, and then I'm going to say, I think it's default. I'm going to do something else. Okay, I don't know what yet. Not allowed. Okay, fine. So what I want to do, well, if it's a digit, I want to move on to the next token. Now input right now is not, well, drop first returns my input. Okay. Yeah, I don't think this is going to work long term, but okay, let's just use it. Okay, so if I get an integer, if I see a digit, I want to consume it. So I'm going to say input equals input dot drop first. Okay, so we're skipping over the digit, and then I guess we're going to return an int. Token.int. And maybe there's a room for an unknown, an error. Okay. Dot dot dot. Yes. Okay. I always forget this. Okay. Oh my goodness. Okay. Yeah. Let's do this. Guard character equals input dot first, else return token dot EOF. Okay, so I can switch on the character. It should be unwrap. Let ch equals that. Okay, will never be executed. Correct. Okay, run this. Okay. That's one digit. Well, I may delete the extra tests in a moment here. multiple digits returns X int. Okay. I think this will show the problem I'm anticipating. This should fail. Also, I'm not catching the 9, and that's kind of a problem. Oh, it pulled off the 9, but not the value. Okay, so let's... okay, and then I think our type, just like we did... where's AST? Just like we did this stuff, we're going to do the same thing again. We're going to put the type int, okay, the value. I'm not going to include the type yet because I'm not going that far. I'm just doing this much. Okay, so the token is not going to know anything about types and all that stuff. That's assigned later. At least the way I'm anticipating doing this, I'm trying to just be low-level syntax and get through the file. Okay, so I just need to put the value in there. Where's Lexer? Okay, so my token int is going to have an extra value, and it's an int. Okay, and so I should be able to say this. Well, let's just do 0 for now. And I'm going to say token.int is result. How do you pull that out? Oh my gosh. Can we get the value directly? I guess the value is the type, but we got to do that. Okay. I'm surprised it'll let me do this, but I'm going to say this, 9 result. Okay, int has no associated values. That's not true. At least if I did it right. Required token conform to equatable. Okay, we will make that happen. And I don't know, did we do that in here? Where's AST? Oh yeah, we get it for free. Oh, lovely. Okay, or mostly free. Extension token. I guess I don't have to do anything then. All right, try again. Token.int of 921. All right, I think we're going to get our failing test. int9 is not equal to 0. Okay, yeah. And this, we can just say lexer.get. I don't think the result's adding anything. Okay. Yeah, so now... Well, this is where we got to be... So, like, I don't want to be copying these things around, but I'm going to for now, and we'll nudge our Lex input to be a little more helpful here. So I've got the character. I'm going to I'll make a variable that's the number is just character for starters. Okay, and then I'm going to make a new int. I think I can just pass this array in, can't I? No. As int of a string of number. Try that. And I guess I'm guaranteeing it's an int. So we'll take it for that, and we'll deal with that part later. So I want to pass the first Lexer test, and not the second one, or first number test. Yeah. Okay. So we're growing our rule. So I guess we're going to say a number. Well, an integer is 0 through 9 plus. Okay. So if we know the number is, if the character is 0 through 9, we're good. Okay. And so we can do this array of character. Okay. So what I'd like to do is I'd like to say while the character let's see, 0, 9 dot contains character. What am I going to do? Well, I'm going to accumulate it. Cannot convert value of closed bool to expected condition type. Is it a reference thing here? Parentheses. All right. And then now my new, I got to get another character out. Character equals, and this is where we get kind of stuck. Okay. I want to do input dot first, but I got to deal with the fact that I might get a token error at some point. So let's just take input dot first. And I don't know, can I do this? I want to get the right blow up. Cannot. Oh. Can I make this a var? Okay. Yeah, we're gonna see some blow up. Okay, so unexpectedly found nil while matching a blow up, or matching a optional. All right, because I said input dot first will be a character, and it's not. It's end of the string. It's not a character. So I'm gonna make a change in my my input. Is that in parser? I think still. Okay. If you ask for character, it returns input dot first. Let's find the users of this. Callers. Lexer get match and skip to. Where's first? Oh, first not equal end value. Okay. End value is a character. We let it do that comparison. Yeah, so what I want to do, I think I can do this safely. So I'm going to say um, must return a character. And I'm going to say if it's well, what I want to do is say if input.first exists, if input.first is not nil, then input.first. Otherwise, I'm going to return a null character. And cannot convert string element optional character to return type character input.first. Bang. Okay, if it knows it exists, return it. Okay, and is it /u? Yeah. Expected hexadecimal braces after this. Okay. I don't think I need anything more than that. All right, and then the only use of it that cares is this one. So we want to get character equals input dot first. And then input dot first not equal. And I'm going to say my input dot EOF. Since I'm using that EOF thing, okay. Var EOF, well, let EOF be a character equal to /u 0. Okay. My hope is all the existing tests still pass. We may still have some errors in ours. It might make them pass too, though. Oh, didn't build. What's your problem? Okay. Let's do it this way. Let character equal input dot first. If character equals my input dot EOF, we want to return nil. Okay. And that's the old way. This is member input. Okay, let's. Is it static? Let. Okay. Static member EOF cannot be. Okay. All right. Is that still legit? Rest.first. Now, this is a little funny because it was always looking for a character. All right. Character equals input dot first. Okay, yeah, we changed the way it worked. Okay. Now we're no longer optional. Okay. Have I got everything? Yes. Okay. So this is using a Sentinel. I don't know if the Sentinel, if like in Swift, a null character is a legit character in the input file. I'm going to assume it's not an Elm. if it really mattered, we could, well, we would certainly not care at, like, it would be okay here because the character we're checking, we just want to find out if it's not a digit. If it's not a digit, we don't care what happens to it. But if it is, let's see, if it is a null character in the thing, we would have to muck with this. We couldn't just assume we would return EOF. We would have to take another character and see if it was really the input. We would have to check if it's really the rest of the input is really empty. Okay, we actually have something that can do that, but and then treat it like a space or whatever the language calls for. But in our case, I think we're okay as is. So I'm the only thing I'm going to do is add a 0 in here and make sure it's parsing the whole range of digits. I'm going to drop this test because on one test it's one or more. I don't think we're going to make a mistake there. Well, let's just leave it for now. Okay. So we've got something that either, well, it can find in a file, it can find an integer, or it can find anything else is an error. Okay. Let's go on to float. Now the thing is, the floats start with 0 through 9, so we have to kind of implicitly do all this stuff for that. We can't just say, oh, you saw something that wasn't a digit, return. We have to decide whether to keep going looking for a float, and if it finds part of a float, I don't know. We have to decide what's legit input. I don't think there's a way to say 921. Like, I don't think Elm has ranges. Let's find out. Do I have another window? No, we'll just use this. Okay. Does Elm have ranges? Yeah. Let's try Elm language. Should support higher kind of. Oh, interesting. Doesn't support higher language types. So we would have an issue with we would run into more issues from that. Well, where's the Elm definition? Elm.org, yeah. Where's some docs? Syntax. Looks like it just does that. Like Swift has that ... syntax. This apparently doesn't. Okay, good enough. All right, so in Swift, like right up here, if I see, let's say I didn't have characters, I had digits, I could have 0 ... 9. 0 dot looks like, oh, I'm going to have a float. And then you see dot again, and it's like, oh, no, it's not a float. I shouldn't have even read that dot, so you have to kind of, you have to have a little bit of backup, backing up. We will not worry about that for the moment. All right. So I think we're ready to move on to float. My goodness. Okay. So a float, we got our definition up top. Okay, a float is a bunch of digits, okay, and a dot or an E. Okay, so float is literal dot or literal E or literal upper E. Okay, so if it's in these three characters, then we want to keep going with a float. All right, so let's go back to tests. Okay, so test multiple digits not float returns int. Well, multiple digits, then x returns int. Maybe I can test that in here. Let's check. Yeah. Okay. So let's go on. Func test digits dot digits returns float. And these tests, I don't know, they're already looking. It's looking like we'd like a helper of some sort. You know, we're writing the same test structure over and over. Basically, given a string and a token, find if the tokenizer reads the thing. Okay. So digits 32, 27.32, 34. Who can type? Let's make this something that'll come out even in decimal 75. Binary. Int, this should be float and 27.75. Ooh, we may have to break this one up. Token has no member float. Let's add that. Okay, and should fail. Did I mess that up? Yeah. I don't know. Value works for me here too. Okay. Right. Failed float not equal to int 27. Okay, so you can see it peeled off the front. It hit a character that wasn't a digit, and it said, I'm done. I'll just return the stuff I got. All right. So we got our failing test. It's probably a good time for a break then. Let's take a 2-minute break, and we'll come back and fix the test. All right, see you in a moment. All right, welcome back. All right, so we've got this failing test, and we need to carry on through the tokenizing. Oops, that way, but that way. All right, so the float or they call it float in Elm, is 0 through 9 plus, and then we're going to take the path of dot 0 to 9 plus. Okay, and so we got our input. We exit this loop. Okay. Well, if the character is not a dot, then we need to return this thing. Okay, if character is not period, then return this int. Okay, if it is a period, we're going to keep looking. Okay, so if it's a period, well, in the end, we're going to return token.float, okay, of something. Okay. Otherwise, well, we're going to append number. Now we know it's a period, okay? And we expect more digits, okay? Well, I don't know the answer. Is 3-point a legal float in Elm? I think we may have tried it, but let's find an Elm REPL. 3-point. Nope, I'm looking for, yeah, 3.4 is fine. Yeah. Okay. If the character is, well, now we need to move forward again. Okay, so we got a character dot. We need to drop the dot. And I definitely am not liking this part too much. And get the next character. Okay. And then we're saying while, and same deal. Okay. All right. And then here, we got to put the value in. Well, just like we did up there, we're going to do a double in our case of string of number. Okay. And I think this will pass. Okay. Well, I can see stuff going on already that's going to make things tricky. All right, so, well, we realize that 3 dot is not legit. Let's make that test. Test digits dot returns error. Three dot, we tried. We expect token.error to be the result of lexer.get. Okay, and I don't know how that's going to blow up, but it's not going to work. Maybe it'll blow up in the conversion. Yeah, so they converted it. Oh, they didn't blow up, but they did convert 3 dot. So I guess 3 dot is legal in Swiftland. No. Okay, no syntax error. Expected member name. Well, it's legal in the conversion anyway. Okay. But at any rate, we don't want it, so that makes it a problem. Editor, let's go to Lexer. I obviously keep going the wrong way, so let's swap these around. Lexer tests and Lexer. Okay. If the character is not one of these, if it doesn't contain it, then we got an error. And we're not very sophisticated, but that's okay. All right. I think that'll pass. If it's not a character, digit character, return error. Yes. All right. Let's do some refactoring already. So one is I want a test helper. And I don't know, sometimes test token. We're going to give it an input of string and a expected of token. Okay. And it's going to look a lot like this. But that is our input. And that is our expected. Okay. Usually I call these check. All right. And so we should be able to say check token, nothing gets token.eof. Now, I don't know. I wrote an article a while back about kind of moving from test by test into more parameterized tests, which they don't really support in Swift. And maybe we'll go there too, but let's get this going first. It's a reasonable step on the way. Check token. Yeah, this is already. Don't do it that way. Okay. That should all still work. I haven't been very good about my check-ins, have I? Okay, let's check this in. Let's see. Tokenizer, well, let's call it Lexer to be consistent. Lexer gets integer and simple floats. Okay. And if we look in Lexer, sorry, look in Parser. No, I lost Elm Parser. Lexer, didn't, yeah, there it is. Okay. We got float literal, digit, many digits, and literal dot matches digit, many digits, and optional float exponent. Okay, and you got to have one or the other, I think. If you have just digits, so if I made many optional, if I made the dot stuff optional, then you could have many exponent. Maybe that's the way to go. Okay, Let's add. So I'm trying to think if I can. I think I can do literal dot digits question mark, make it optional, and then optional float exponent. If you have neither, you get an int. If you have both, if you have one or the other or both, you combine them and you get a float. Okay, so um, let's make this optional. Well, you got to have the dot and the digits. Okay, that part's not optional, but the whole thing is. Okay, if character is not a dot, hmm. Maybe I want a Boolean or something. It's a little, I don't know. So I want to say this is optional, but 0 to 9 by itself um, is not a float. And then okay, so if the character is not a dot, that's not really accurate. Okay, because we can allow exponents. Okay, so the way we did this, yeah, I think we want to say this is optional. Okay, and so if the character is not a dot, that's okay. But I don't know. Maybe we already have some stuff going on that is confusing. So, um, one thing is right now this ch is local, and so I would like to be able to extract this and make it like digits, because it appears twice, and it's going to appear again. It's okay. Yeah, we want to make things simpler. So let's move this declaration up here. Okay. And we're going to start, the way we say it is we start with the pump primed. Okay, so we want that first character loaded in, and the state is always you are ready, the character has the right value, and then you can get the rest of the input. So let's do character equals input dot first. All right, and now this declaration, we've already done it when we go into get. Self dot input dot first. Okay. I think that's a refactoring. Yay. Okay, so make, I'll say prime the pump, start the Lexer with the first character. Lexer with the first character already read. Okay. And the reason I did that, a reason I did that, is I want to be able to pull out this, that if you want to get stuff. Well, I almost want to pull out. Yeah, I want to pass in number. Maybe I shouldn't worry too much about it, but it does copy arrays. So I would somehow like this to be a digits method. And I don't know if I extract, what do I get? If it passes in number, I'd be okay. Okay, it dealt with that. I'm going to call this digits. Okay, so it says we know character, it assumes every function we do like this is going to assume character is ready to go. So we know character while it's 0 through 9, then we're going to drop the next character and, prime the pump for the next one. So this will be that. Now this routine looks exactly the same. Okay, and so this should be a refactoring. And I'm going to be top down on this thing. So you'll read it top down. Little helper method. Digits. Okay, and just to be sane. Okay, so we extracted digits method. All right, and I'm going to change this. I'm gonna make number be all this stuff. Okay, so if we read the digits. If it's not a dot, we return token int. Okay, I'm gonna change the way this works. If it's not a dot, I'm gonna keep track of things a little more. So I'm gonna have another variable. Is integer, and it's going to start off false. So it's going to start out true. Okay, we know it starts with a digit. So far it's an integer. Okay, if character is not a dot, okay, and then somewhere at the bottom here, I want to do something that says if is integer, and I don't know, maybe this is good or bad, return this. Okay, if the character is not a dot, skip over. Now the character is a dot. We know is integer is false at this point. Will never be executed. If the character is not a dot, let's flip it. If it is a dot, we're going to do all this stuff. Okay, if it's not a dot, it would stay as integer, we return it. So what I'm trying to do is segregate the matching from the decision about the numbers, but I'm just retaining enough information to know which thing I had. All right, I hope this is refactoring. Okay, and we'll reformat a little. Okay. So if it is a dot, we know it's not an integer. we're going to append the dot, get the next character. If it's a dot followed by something other than digits, we know it's an error. That's right. If it's digits, then we're good, and that accumulates into our number. Okay. We already decided we're a float. Okay. So this takes care of this case. Okay. And I think we're ready for the next case. Let's just push it one more time. It's just a format. Yeah, this process could be a little nicer, couldn't it? Okay. Right. So Lexer tests. Let's go on. Let's test digits. We did digits dot digits, digits dot nothing, just digits. We want to do an exponent. Okay. So let's do digits e digits. Returns float. Okay, so our check token, our input is digits, e, we'll start lower, digits, and our result is token dot float 30. Because 3e1 is 3 times 10 to the first, so 30. All right. And this should fail. Okay, so now this case, it covers the dot. If we get here, if the character is E, then we're going to do something else. Okay, so if it's an E, we're gonna do this stuff. We know it's not an integer. We're going to do these things. Okay, and then digits. I guess, well, let's just do digits. Whoops. We'll add in our error case, check our error case next. Okay, digits number. All right, so we're going to see if the double parser, we got to make sure it does the right thing. But if we get an E, we're going to append the E to the thing and skip to the next character and pull in the rest of the digits. Okay, and I think this should pass, or I hope so. If it fails, it's probably because of the double formatting. Swift seems at least as generous as Elm on that front. Okay, so that's fine, but digits E non-digit should fail. Non-digit returns error. (3ex) returns token dot error. This should, I don't know what it'll do. It should pass, come back with an int instead of an error, I think. Found nil while unwrapping optional. Okay, so the float, just 3. I guess it pulled the E. It found the digits, but yeah, we don't have this clause. Okay. I think it'll pass. Okay. Let's do capital E. Well, this is lower E. This one we don't care, I don't think. Okay. Let's do a case for capital E. 3. Well, that's not the case I want. Let's do this one. 4E2, so 400 digits, upper E digits, returns float. Should fail. Okay. And the reason is this should allow the other E. It should pass. Okay, so this is float with digits, E digits, either case. I really wish I could get it to default to that. Ugh. That extra click is so annoying. Okay. Now, the case we haven't talked through. This, we have E or E digits, 0 to 9 plus, and that's optional. Okay, so you go through the digits, you pull off the front, that first one. Now if you see a dot, you say we're no longer an int, we're a float. You accumulate the dot and the digits. If you see an E and digits, we accumulate those. You can have digits, dot digits, digits, dot digits, E digits, digits, E digits. Okay. We haven't dealt with the combo case. This case I think should just work. Okay, so this is digits, dot digits, E2 should become 450. All right, and digits dot digits, E digits returns float. Should pass. Okay, so we will commit this. Okay. Wow. So I'm nudging towards, well, I'm nudging towards where we left off. And the question is how far to push this thing to kind of clean it up. So digits writes into the number array. I'm seeing this, right? These two lines are duplicated multiple times. And actually it's even these 3 lines, and maybe that's enough to Maybe that's enough to justify it. Do I have it up here too, or down here? Number append. No, I do the drop first thing. No, wait. Number append. Drop first. Character equals input dot first. Yeah. This is its own thing, I guess. It's accumulate. Gather. I want to do something that says I'm gonna take this character and save it. Match. Keep. I'm thinking that's right. Okay, so this, I got some value. I'm going to take the input is off my class, so I'm going to refactor this to a method. It should pull ampersand again. Good. I'm going to keep number. Do I need the character? I kind of want it. Okay, let's do keep character number. I wish I could configure where the extracts go because I get tired of moving them. Okay, so keep ch of character number. Number dot append ch. Oh no, I can't do that. I got to leave this character around for things. Keep it into number. Okay. I'm doing the same thing here. Number append, input that. Keep number. Keep number. Do I have one more? Down here. Keep number. Okay, so while your character is dead, you're going to keep it, and that sets up your next one. I think that's okay. I can't let digits just return the token. No, got to have the value for it, so you can't create them very easily. Okay. I got to say, numbers are usually about the most horrible token in the language for most languages. Okay, so we've refactored. Okay, so extract keep that retains the current character and gets the next one in place. Alrighty, let's see. So I don't know how much tighter I want to try and get this, but we can keep going. There's more than just E. You can also have a plus or minus, and that's going to be plus or minus question mark. Okay, and that just feeds in as well. So let's put some test cases in there. Test digits E plus digits returns float. Our input is 4e plus 2. Well, I guess it's okay to be the same. Okay, e plus digits returns float. We got e, we keep the e. Well, if the character is a plus, then we're going to keep it and consume it. And if following the plus is not a 0 or 9, then we got an error. Okay, I think we'll verify that, but it shouldn't be affected on the test. Okay, so this should be okay. All right, and let's add minus. E minus digits. And again, I'm just going to switch to something I know can be represented. So 5, 1 to the right will be 0.5, so 0.05. Is that an exact one? E plus 2. Oh. Should be a syntax error, I think. Yeah. Okay. If character is plus or character is minus. All right, and all right, so we handle digits, digits, e plus minus digits. And then just like before, we got to make sure that if we're going to validate that if you just did 3e plus x or whatever, that it's not valid and it gets an error. But I think this is a confirming test because the way we did it, it should already work. E digits minus non-digits returns error. E5e minus is an error. Please pass. Okay, commit that. Check that 45e minus is an error. Now, so here we get to the heart of what's going on. So, if well, I think we've got a good query here. I mean, this regular expression, that really is well, our comments one will be ugly too, but this is about the worst we'll see. And the code here is ugly enough, but it's tolerable. I think I can extract it. And if I can, that gets us a top level view that's pretty good. Yes. Okay, and we'll call this number. Well, let's Yeah, let's see if it bites. I don't know if the method name and the variable name can be the same. Okay, apparently that's all right. Okay. Well, if there are any human people who want to chat, I'd appreciate it knowing you're there. Any questions so far? But this, well, let's pull this down to my rare comments. All right, so if you're empty input, you get an empty token. Otherwise, if you're a digit, we're going to parse lex you as a number. Otherwise, you're just in error because we don't know what's going on. And then we got some helper functions. I think the helpers maybe go down. You know, I kind of like a top to bottom read for something like this. This get is the high level thing. It's going to be a big case statement of all the prefixes of valid tokens in Elm. And each one will get its own method that basically parses and returns either a token or an error token. And that's pretty much where we are. All right. Oh, I see. My clock just rang 11. We've gone a while. Let's take a 2-minute break. We'll come back and tackle the next thing. But I think we're kind of getting there. All right. See you in 2 minutes. Welcome back. All right. So we have Lexer that knows these tokens and it knows how to produce them. It basically handles floats and number, or floats and integers. And we still have the remnants of Elm Parser around. Let's modify. Oh, interesting. Elm Parser. Who's calling this? Or referencing it, I guess. Find selected text. Okay. Integer tests and interpreter. Okay, so parser, interpret number. Okay, I guess what I would like to do, I could go on and do the comments, but I think, you know, I want to do these incremental things. And the first thing we did last time was get the interpreter working for the simple numbers. So I think I want to do the same thing. I want to say, well, I kind of want there to be an Elm parser. Create the Elm parser and parse my input. That seems like something I can do. I just want to say parser equals Elm parser, new Elm parser. And let's see. I don't know if I want to bust up Elm parser just yet. So let's make a new one. I'm going to put it over here. You're probably spinning around by now, but let's make a class Elm parser. And sorry, my Elm parser for now. I'm going to get rid of the other one eventually, but we're trying to switch things over. So I'm going to say Elm parser and then go back to my test. And they said parse new Elm parser, parse my input. Okay, we'll just pass in the string for now and call interpreter. So let's function test interpret. Sorry. Let's just get this. I'm going to call this old. And this thing is going to say let parser equal my Elm parser of 739. And Let AST equal parser dot parse. Do I want to pass the input there or in the constructor? I don't know. But I do want this all to be true. Okay. Where's parser? Class my own parser. Okay, let's build. Succeeded. All right. And then this test should fail. Interpreter tests. Okay, constructor. Okay. Well, we got. I think we really want to make. We want to set up the Lexer, so it's going to be more like this. Okay, so we're going to say Lexer equals Lexer of string. Okay. And then we provide a method parse. Returns NAST. And let's see, AST. I don't know if it has a nothing. Elm ignored. Okay, let's do that. And we don't need a return statement when it's like that. Apparently we have to say AST dot though. Okay. Should fail, right? Should come back with AST ignored. Okay, just the one interpret number. Okay, 739 is not equal to empty string. Okay, so let's see, our parse then. Okay, parse gets fancier. So what he's going to do is let token equal lexer.get. Okay, and then case switch. How do we do these switches? Switch token. Okay, one case is we got an error. Can I say this here? Do I have to put the dot? Okay. Let's return AST.elm ignored for now. Case int let value. I've typed that quote for that colon so many times. All right. We should return AST dot elm integer value and elm types dot number. And then default, let's return AST.elm ignored. Cannot find error. Token dot. Had my hopes up. Token dot. All right. Should pass. Okay, and then let's write the next test. So interpret number, I guess I'm satisfied my new approach covers that. All right, now interpret float. Let's duplicate that. Here's the old. Okay, interpret float literal. It's going to start the same way. Well, okay, it's going to start with these two. Interpret float 42.5. I don't know how I got there, but okay. Yes, that should be fine. Should fail. We should get Elm ignored. Empty string. Yep. Okay. I guess our method's going to be very similar. Token integer. Well, the other case is token dot float. Let value. Exhaustive. What's not in there? Token. Oh, EOF. Okay. I guess we'll let EOF be ignored as well. Let's pull these to the bottom. No, let's put it explicitly. Token.eof return ignored. Okay. Now it should pass. Nice. Okay. Let's see. Parser. I guess I got rid of that one. All right. So interpreter tests. We have float old. We don't need it anymore. Okay. And now we've got input. Well, we don't really need the difference here because now we have one parser that does everything. And that was where we were headed eventually in the other way too, but we were building up the pieces. But I will take this moment to refactor an expression out of that thing. So let's just delete this. It's doing the same thing. And where's my parse? Well, let's keep this much. I want a method that, just like I did my tokens all primed, ready to go, I want to do the same thing here. And basically, I want to say switch token if it's an int or a float. I'm going to keep this much. It's kind of a weird extract. Forgive me. Okay, function expression is going to yield an AST. And I'm going to keep this much. And default. Okay, so I'm just going to let those float out, and I'm going to make this a variable again, and pull it up into the initializer. Okay, so my assumption is whenever you go in to parse, you're starting with token ready to go. And the same thing should be true here. All right, let's run this. Failed. Did I leave out a brace? My Elm parser, function parse. Yes, I did. Okay. Well, I didn't have any failures because, oh wait, I haven't run it. I won't have any failures because I haven't called it. All right, let's call it. Okay, so I want to do, whoops. Well, I want to do this. I don't think I have to be more precise. Return expression. Is that gonna work? So like that. Do I do a comma? Okay, so we did a refactoring. Extract expression. Okay. Right. Now my interpreter tests are minimal but okay. Let's see what else. What can we get rid of now? I should be able to get rid of just about anything involving those floats. Okay, where's my files? All right, so let's look in Lexer. I don't think anybody should be referencing this. There may be a test. I don't see callers. Let's comment it out. Well, let's just comment all these out. Expression tests. Well, we don't really need this test anymore. We've already tested these values as they come out from the tokenizer, and then well, is that true? We want to change this test, I guess. Do I want to just call expression directly? That's my question. Yeah, I think that's probably a good thing to do. So let's get our parser tests, wherever those went. Integer tests. Okay. Digit matches multiple digits. We certainly did this test. Did we do this test? Well, we don't need to really, because it's not going to get reported as an integer literal. It's just going to be like, no, we don't qualify for that. We only switch on 0 through 9. Same thing here, end of string. So integer tests can go away. Maybe this cleanup is the ending point here today. Shoot, let's cancel that and make sure I saved it and then delete it. Delete. Okay. Now, what else we got? Failures. Check parser rejects. Parameter A could not be inferred. Expression tests and float tests. Let's see what we got here. Well, okay. Let's make sure. We want float tests, and then we had Lexer tests. Okay, so digits.digits, that's the first one. Digits, e digits. Digits.digits, e digits. Yep. E plus digits, e minus digits. Okay, so float tests can go away too. Float tests will delete. Now expression tests. Well, I think he's kind of redundant. The only place I'm going like, oh, maybe not quite, is the fact of once you parse the expression, you have to be ready for the next thing, and we don't handle that. But I figure our next test is going to expose that anyway. So I think we can just delete this. We're in effect, our parser handles this case because of the work we just did to extract it. So I think that's okay. We're not testing the rest, but I'm going to let that go. Okay, delete this, move to trash. All right, make sure everything runs. And let's go back to Lexer. Okay, now we got a bunch of commented out stuff. Let's get rid of it. Okay. Integer literal, we can get rid of that one. Whoops. All right. We haven't dealt with this comments yet, or spaces, but I think we can do that next time. All right, and make sure this runs. So this is eliminate, how small this is. Dead code for old way of handling integers and floats. All right, well, we will pick up there next time. It'll be tomorrow, Thursday, the 28th, 1 to 3 p.m. Eastern time, as always for me anyway. And I will see you then or another time, I hope. Thanks for joining me. Bye-bye.